Students, today we're going to have a look at a disconnection problem, and I'm going to do one of the examples from your textbook, and that example is going to show you how to disconnect a molecule with two functional groups on adjacent carbons. We're going to look at propranolol, which is a drug, and that is going to have two functional groups on adjacent carbons, and we're going to see how to disconnect that particular molecule, break it down into smaller fragments, and then build it up again. So the drug that we're going to look at has a structure like this with a net power group, and this is taken straight from your textbook for the course. And has an oxygen at that position. It has two carbon atoms in a hydroxy group, and then an amino group here, the isopropyl group in that position. And we're going to look to disconnect this molecule. And the first thing that we look at is look for heteroatoms in the molecule, and you'll see you have a heteroatom here and a heteroatom there, which means that you can disconnect along here, and along here. It's highly unlikely you're going to disconnect here because you have no known reaction to put that oxygen onto the aromatic ring. Remember that nucleophilic substitutions onto aromatic rings only occur if the aromatic ring is deactivated. So I'd look to break this OC bond or this NC bond, and I'd rather look to disconnect here. If I disconnect here, what normally happens is that firstly I am separating the more reactive nucleophile from the rest of the molecule. And if I do that, I don't have to worry about that nitrogen nucleophile in subsequent steps, as if I added it at the beginning of the synthesis, I would have to worry about it in each of the subsequent steps. The second thing is that I have a 1-2 relationship between the hydroxy functionality and the NH functionality, which means that both these functional groups are on adjacent carbons. And whenever you see this type of pattern and you see a hydroxy group, we can disconnect directly to the epoxide. Remember that this would normally be the positive carbon, and what I'm going to do now is disconnect it straight to the epoxide. You can see that I've kept the carbon atoms intact. If I had to number this, there's still carbon number 1, carbon number 2, and there's the carbon bonded to the oxygen. Carbon number 1, carbon number 2, carbon bonded to oxygen. So I've kept all the carbon atoms intact, and there's my nucleophile. So I have now disconnected the more reactive nitrogen nucleophile. I've also disconnected to an epoxide, which is very, very useful because these epoxides are generally available commercially. But I can break this up further by looking now at the other heteroatom, and this is this oxygen here, and that oxygen carbon bond can be broken very simply so that would normally disconnect to the hydroxide or the alcohol, and that carbon atom that you see here would disconnect to the chlorine molecule or the chloride, and this molecule is called epichlorohydrin. Epichlorohydrin is a very useful synthetic reagent. So you've disconnected your molecule into that and that, disconnected that further into that and that. I want to show you briefly what happens in this reaction, because that reacts with that to give you that intermediate, but the reaction doesn't really occur by nucleophilic attack of that oxygen onto this carbon. In this epoxide, the most reactive carbon atoms are those within the epoxide, which means either that carbon or that carbon, and more often than not a reaction occurs at the less hindered carbon of the epoxide, which is this particular carbon that you see here. So let's look a bit closer at that reaction and see how that actually occurs. The oxygen nucleophile would attack the epoxide, and as I said, it would normally attack the less hindered carbon of the epoxide, which means an attack on that particular carbon, and that would give you this intermediate. You have an oxygen atom bonded now to a carbon atom, and that's bonded to two other carbon atoms, 1, 2, 3, so 1, 2, 3. And now I'm going to place my oxygen atom and my chlorine atom on this intermediate. And watch how I do it. This chlorine atom is on the terminal carbon, so I place it on the terminal carbon. When this epoxide opens up, this bond breaks, and the O- now lies on the carbon adjacent to the chlorine atom. So that should be a chlorine atom. So that's 1, 2, 3 carbons, 1, 2, 3 carbons, and there's my chlorine atom here. Right, so the carbon on the chlorine, and the carbon with the oxygen, and then the carbon with the other oxygen that you can see forms that bond. And in the subsequent step, that oxygen attacks this particular carbon, and that chlorine leaves. And if we look at the product that we get, as an oxygen, a carbon atom that's not formed in the epoxide, and then a carbon atom that is formed in the epoxide. So we have 1 carbon atom, 2 carbon atoms, 3 carbon atoms forming the epoxide ring, and that is the same molecule that you see here. The next step would be for this nitrogen nucleophile to then attack that particular carbon, epoxide again opening up. Ultimately, after protons are moved from here and added to that oxygen, we would get our target molecule, which looks like, just remember, this oxygen carbon bond is not broken, and then we've got the other carbon atom to which the nitrogen atom is attached to. As I said, 1 hydrogen leaves there and adds onto here. You can see it there. And that's your molecule. So hopefully that shows you how we disconnected a 1,2 or molecule with 2 functional groups on adjacent carbons, and this is a good example of a 1,2 disconnection. And more often than not, when you do this, we can actually write something like this onto the arrow 1,2 di-X, meaning a 1,2 disconnection, and that's when there's a relationship between 2 functional groups on adjacent carbons. So I hope you enjoyed this example and you learned a thing or two, and look forward to the next one.